Hello guys, I'll be the lecturer for the AP Calculus BC online lectures. This is the first lecture out of 4 lectures, which will focus on limit. So how are the lectures structured? Our main textbook for this course is Calculus: A New Horizon combined by Howard Anton, and I believe that this series of videos will be a crash course to get a 5 in the AP Calculus BC exam, which we always strive for in any AP exams. And if you score satisfactorily or 3 or higher in the actual exam, you will be able to get college credit in your college of choice. So, as I look into the past exams, I made an average cutoff for 3, 4, 5. So the average cutoff for 3 is 41 out of 108, which is around 38%. Cutoff for 4 is 54 out of 108, which is 50%. And cutoff for 5, which we always strive for, is 67 out of 108, which is 62%. You might notice that these cutoffs are really low, but the content itself is very difficult, which will make the cutoff lower. So the topics to cover in this lecture are AP exam structure, definition of limit, 3 ways to compute a limit, limit rules, one-sided limits, continuity, discontinuity, and types of discontinuities, squeeze theorem and its applications, intermediate value theorem, or IVT. So to introduce next year's exam, the exam date will be Monday, May 12th, 2025 at 8 a.m. local time. So please don't forget the exam time. And next year, surprisingly, will be the first year that the exam will be digital format. So basically, you complete the multiple choice questions on the built-in Blue Book app that is made by College Board, and you see the questions for the free response questions in the Blue Book app. But since Calculus BC exam requires symbolic notation such as graphing, you will handwrite these answers on a separate sheet of paper. So there are 2 sessions for multiple choice questions and 2 sessions for free response questions. For MCQ, multiple choice questions, there is section 1A with no calculator, which is 30 questions in 1 hour, which comprises of 1/3 of the overall score. And there is an MCQ section with calculator. And surprisingly, College Board allowed to use Desmos calculators, which are built into SAT, but I guess they extended into APs. And these calculators are built into exam applications, so you also want to bring a graphing calculator that you have, but if you don't have it, there is always a Desmos calculator, which is very comfortable to use. And there is 15 questions and 45 minutes in section 1B, and it will comprise of 1/6 of your overall score. For section 2A, it's the start of free response questions with calculator. So unlike MCQ, the calculator section comes first. And there are 2 questions and 30 minutes, which comprises of, again, 1/6 of overall score. So with calculator, it comprises of 1/3 of the overall score. And for section 2B, there's an FRQ without any calculator. And there's 4 questions in 1 hour, which comprises of 33.3% or 1/3. So no calculator comprises of 2/3 of the overall score, and calculator sections will comprise 33.3% or 1/3 of the overall score. Now let's get right into the content. So the first concept that I'm going to introduce you is called the limit, and denote it as limit at x goes to k of f of x, or f of x is a function, is L, where k is a real number. So, or k can be infinity or negative infinity, but usually AP exams will not test these infinity to negative infinity, but it will mostly test a real number. So it means that as x gets sufficiently close to k, but it's not equal to k, because k might be infinity or negative infinity. So if, for example, if k is infinity, then as x gets larger, so as x gets larger, f of x reaches a value of L. So where L might be a real number or L might diverge. Yeah, limits may not exist due to oscillations, and which occurs mostly in trigonometric functions due to divergence. So for example, what I mean by divergence is, for example, if you had a function y equals x, and if I find the limit as x goes to infinity, or y equals x, then it does not exist because due to divergence. And also remember that infinity is not a number, it is just a concept. It's not a limit. So basically, if you consider f of x as x squared minus x plus 1 graph, you can see these values from left side and right side from 2. So basically, you're finding limit as x goes to 2, x goes to 2 of f of x, and we are considering both sides, left side, so values that are less than 2, and right side, there are values greater than 2. So this is the right side, and this is the left side. So as you can see in this table below, you can see that as x gets to 2, f of x eventually gets to a value of 3. So we can, since it's a quadratic function, we can just substitute these values. So 2 squared minus 2 plus 1, which will obviously get a value of 3, but still it is a limit. So as x approaches 2, f of x approaches 3. What I mean by oscillations is if you consider the limit as x goes to 0, sine of pi over x, and that is the graph above, and x, the table describes 1 radians to until it approaches 0 radians, and pi over x, it reaches a value of, it approaches a value of infinity because it increases by a factor of 10 times pi. And this graph shows that as x equals 0, the values of sine pi over x oscillate between -1 and 1, right? With increasing rapidity. So we don't know as x equals 0 whether sine pi over x will reach attain a value of -1 or 1. So we can't predict. So the limit does not exist due to oscillation. There are mainly 3 ways to compute a limit. First, by direct substitution, as explored in the quadratic function example, x squared minus x plus 1 example. And some examples that you can directly substitute these values is limit x as x goes to 0, x squared plus 4, or limit x goes to pi over 2 of sine x. The second way is algebraic manipulations, which includes factoring and using conjugates. So one example is limit at x goes to 1, x squared minus 2x plus 1, everything over x minus 1. Or limit x goes to 5, square root of x plus 11 minus 4 over x minus 5. And the third way is to use trigonometric manipulations, in which you use trigonometric identities such as double angle, triple angle, half angle identities. So for example, limit as x goes to 0, sine of 2x over x squared, or limit as x goes to 0, 1 minus cosine 3x over x squared. One simple tip is to use direct substitutions first, and if the expression is in indeterminate form, or for example 0 over 0, or 0 over infinity, or 0 to the 0, or infinity to the infinity, or infinity to the 0, or other similar forms. If the expression results in k over 0 for some non-zero number k, so for example, if it reaches a value of 1 over 0, for example, which we can't define, then the expression is undefined, and thus the limit will always not exist. So the limit rules, it may seem self-explanatory, but still let's go over the rules. Let limit stands for one of the limits. This basically limit as x goes to a, limit as x goes to a minus, which we'll learn later in this lecture. Basically, what limit x goes to a minus and x goes to a plus means that, for example, and if here's a, limit as x goes to a minus is the value it approaches from a value smaller than a, and limit as x goes to a plus is basically if you approach from a value bigger than a and you almost reach a value of a, like that. Or limit x goes to plus infinity, or limit goes to x minus infinity. So if L1 equals limit f of x and L2 is limit g of x both exist, basically it doesn't diverge, it doesn't oscillate, then limit fx plus gx equals limit f of x plus limit g of x equals L1 plus L2, and it's very similar for fx minus gx. And limit f of x times g of x equals limit f of x times limit g of x equals L1 L2, and same goes to division, only if L2 is not equal to 0, because we can't divide by 0. And limit the nth root of f of x equals nth root of limit f of x equals nth root of L1, provided that L1 is greater than 0 if n is even. So, theorem. For any polynomial, p of x equals c0 plus c1x plus c2x2 x squared plus cnxn and x to the n, and any real number alpha, limit as x goes to alpha, p of x equals c0 plus c1 alpha plus c2 alpha squared plus cn alpha to the nth power equals p of alpha. Basically, we want to prove to you that direct substitution works for any polynomial expression. Proof. Limit as x goes to alpha, p of x equals limit x goes to alpha. We substitute these values in, and by the property that I explained to you last slide, we can divide all the limits into limit as x goes to alpha c0 plus limit x goes to alpha c1x, like that. And we can put the coefficients outside of the limit, so we can modify into c1 times limit x goes to alpha x plus until cn times limit x goes to alpha x to the n power. So, which leads to c0 plus c1 alpha plus until cn alpha to the n, which equals p alpha. Moving on to actually computing these limits. Direct substitution is self-explanatory. You just substitute the values in. Remember, for any polynomial function, direct substitution works. So, for example, if its limit x goes to 0, x squared plus 4, we can divide these into two limits, and we just add 0 plus 4 equals 4. And similarly for sine, limit as x goes to pi over 2 of sine of x, we just substitute x for pi over 2, which gives us 1. The second method is to factor the expressions, provided that the expression is factorable. So, for example, as limit x goes to 1, x squared minus 2x plus 1 over x minus 1. If you just substitute these values in, you will get an indeterminate form of 0 over 0. But the fortunate thing is that the numerator is factorable into x times 1, x minus 1 squared over x minus 1. So we can just divide these values by x minus 1. But you might think, why divide by x minus 1 if x is 1 and x minus 1 is 0? Remember, in this limit, we know that x is not equal to 1, but it's approaching 1. So basically, it is approaching 1 that is from a value that is not equal to 1. So we can divide it by x minus 1, which gives us a polynomial expression, and which we use direct substitution to get 0. And we always use conjugates if the expression involves nth roots. But in the AP exams, nearly all of the problems only use square roots, so you don't have to worry about cube roots or any other roots. For example, limit as x goes to 5, square root of x plus 11 minus 4, everything over x minus 5. if you directly substitute again, you will also notice that it will result in an indeterminate form of 0 over 0. So what I mean by using conjugates is multiplying the numerator or the denominator, where whatever the square root is in, by its conjugate. So if, for example, if the expression is square root of x plus 11 minus 4, the conjugate is square root of x plus 11 plus 4. And since we're multiplying the numerator, we also have to multiply the denominator. And you will notice that these this product will result in x minus 5, and the denominator is unchanged, in which we can divide by x minus 5 because it is a value that is not equal to 5, rather that is approaching a value less than or greater equal than 5. So it will result in 1 over x square root of x plus 11 plus 4. And if you directly substitute the values, it is not in an indeterminate form, and so you can directly substitute it, which equals 1/8. What I mean by trigonometric manipulations is to use trigonometric identities you know about. And here there are two limits to know. Limit as x goes to 0, sine x over x equals 1, and limit as x goes to 0, 1 minus cosine x over x is 0. The proofs are too difficult in this course, so you just need to know these two limits. So for example, we are asked to find limit as x goes to 0, sine of 2x over x squared. And by the double angle identity, we know that sine of 2x equals 2 sine x cosine x. And we can split these into three separate limits. And if you multiply these three, we'll get the same result. So that's why we're allowed to split it. And limit x goes to 0 is 2. And limit as x goes to 0, sine x over x is 1 here. And limit as x goes to 0, cosine over x is 1 over x. And which will be like this. 2 times limit x goes to 0, 1 over x. But the thing is, limit as x goes to 0, 1 over x does not exist, because from the right side, this is the graph of 1 over x. From the right side, it approaches a value of infinity, but from the left side, it approaches a value of negative infinity. So in either case, it diverges, but since we were diverging into different values, it does not exist. As also, if you just directly substitute, the numerator is non-zero while the denominator is 0, so it'll be undefined. So limit of x goes to 0, sine over 2x over x squared does not exist. So one-sided limits, basically what it means, as I mentioned earlier, is if the values of f of x can be made as close as we like to L by making x sufficiently close to a but greater than a, then we write limit as x goes to a plus f of x equals L. So these values are all, if you set this value as a, these values are all a plus. And similarly, if the values of f of x can be made as close as we like to L by making x sufficiently close to a but less than a, then we mark these values until right before a as a minus. So basically, this is the range of a minus, and this is the domain of a range of a plus. So if you consider f of x equals absolute value of x, everything over x, which is shown below, notice that limit as x goes to 0 minus f of x equals -1. So like we're only considering these values. And limit as x goes to 0 plus f of x equals 1, so these values. But the thing is, as limit x goes to 0 minus f of x does not equal limit as x goes to 0 plus f of x, we can't conclude the limit as x goes to 0, so it will not exist. So we can make a theorem that if limit as x goes to k minus f of x does not equal limit as x goes to k plus f of x for some k a real number, then limit as x goes to k of f of x does not exist. Hence, if limit as x goes to k f of x equals L, if and only if limit as x goes to k minus f of x equals L equals limit as x goes to k f of x. I'll introduce you a new concept called continuity. Basically, a discontinuous curve is a curve that has breaks or holes. So for example, limit, as I said in the last slide, absolute value of x over x has a break at x equals 0. And this is called a hole. And for continuous, it's a curve that is not discontinuous, so it's very smooth and it has no breaks or holes. So there are 4 types of discontinuities. First is a removable discontinuity. Basically, if limit as x goes to k minus equal f of x equals L equals limit as x goes to k plus f of x for some k in the set of real numbers and function f of x, but f of k is not defined. So basically, we can removable discontinuity is also called a hole. So here, if for example it's like here is f of x, but we can see that limit x goes to 1 minus and limit x goes to 1 plus f of x equals 1, but f of 1 is not defined because there's a hole. The hole is called a removable discontinuity. Infinite discontinuity is limit x goes to k minus or limit x goes to k plus f of x does not exist due to divergence. So here, if you put y equals 1 over x here, either way, limit as x goes to 0 minus 1 over x or limit as x goes to 0 plus f of x, it will not exist due to divergence. And basically, y equals 1 over x has an infinite discontinuity as x equals 0. So jump discontinuity means is a break that I mentioned in the last slide. So basically, if you consider absolute value of x over x again, it has a jump discontinuity as x equals 0. So limit as x goes to k minus f of x does not equal to the value of limit as x goes to k plus of f of x. And oscillating discontinuity is basically limit as x goes to k minus f of x and limit x goes to k plus f of x does not exist due to oscillations. And this is a graphical example of types of discontinuities. Removable discontinuity is just a hole. Infinite is going to infinity or negative infinity. Jump discontinuity is just a break, and oscillating discontinuity is an oscillation at a specific point. Now, squeeze theorem. Let f, g, x, h be functions such that g of x is less than or equal to f of x, that is less than or equal to h of x, for all x in some open interval containing the point C, with the possible exception that an equality does not need to hold at C. If limit as x goes to C, g of x equals limit as x goes to C, h of x equals L, then limit as x goes to C, f of x equals C. So basically, in this graph, if you let we can identify g of x, f of x, and h of x. So the orange graph here at the bottommost graph is g of x. And the blue graph at the middle is f, and the top part is h. So basically, if g, what the theorem says is g and h, if f is between g and h reaches the same limit at a specific point, then f must reach the same limit in the same point. So we can use the squeeze theorem to compute limit as x goes to 0, x squared times sine 1 over x. Take a few seconds to solve. Pause the video if necessary. and please solve it. Okay, so the first step is that -1 is less than or equal to sine 1 over x, which is less than or equal to 1, right? Because the range of sine x is -1 to 1, and sine 1 over x, the range wouldn't change. So if you multiply all of the inequalities by x squared, -x squared must be less than or equal to x squared times sine over 1 over x, which is less than or equal to x squared. But the thing is, notice that if you do limit as x goes to 0 minus x squared and limit x goes to 0 positive x squared, they will both equal 0, right? By direct substitution. Since x squared sine 1 over x is between these two functions, and minus x squared and x squared as limits x goes to 0 both equal 0, x squared sine over 1 over x is less than or equal to 0, and also less than or equal to 0, which means that it must equal 0. Now, I'll introduce you to a new theorem, intermediate value theorem. If f is continuous on a closed interval a to b, inclusive, and f of a is less than or equal to k, and k is less than or equal to f of b, then there is at least one number x in the interval a comma b inclusive such that f of x equals k. So basically, between a and b and specific of y value between a and b, there must be at least one point satisfying such that f of x equals k. So for example, if f of x is modified to a function like this or this, there is at least one point such that f of x equals k. And one corollary follow of theorem is that if f is continuous on a closed interval a comma b, and f of a and f of b are both non-zero, and f of a and f of b have opposite signs. So for example, f of a might be greater than 0, which means that f of b must be less than 0, or f of a is less than 0, then f of b is greater than 0. Then there must be at least one solution of the equations f of x equals 0 in the open interval a comma b, which does not include a comma b, because a and b are both non-zero. So for example, even if f of x is changed like to this or like this, you can see that f of x equals 0 in at least one point. So there is at least one x-intercept in both of these functions. So I'll give you an example problem. Pause this video if necessary to solve it. Suppose f of minus 1 equals 4 and f of 4 equals 7. Can we use IVT, intermediate value theorem, to conclude that there is at least one x in minus 1 comma x such that f of x equals 6? You may say yes, but the answer is no. Why? The problem never said that f is continuous. And one requirement, as I said in the previous slides, is that f must be a continuous function. Now, assume that f is continuous, and can we use IVT to conclude that there is at least one x in -1, 4 such that f of x equals 6 now? And now the answer is yes, since f of minus 1 equals 4 and f of 4 equals 7, and 6 is clearly between 4 and 7, we can use IVT to conclude the claim such that there is at least one x in -1, 4 such that f of x equals 6. Now we'll move to AP problems. At the later parts of every lecture, I'll select some past release AP problems and present full solutions for each of them. There will be 4 problems today. The problem 1, line y equals 5 as a horizontal asymptote to the graph of which of the following functions? A, y equals sine 5x over x. B, y equals 5x. C, y equals 1 over x minus 5. D, y equals 5x over 1 minus x. E, y equals 20x squared minus x everything over 1 plus 4x squared. Pause this video if necessary and solve this problem. Okay, so the answer for problem 1 is E. So let's go over choice A, sine 5x over x. So basically, horizontal asymptote is, we'll have to check the limit as x goes to infinity. So as x equals infinity, sine of 5x oscillates between -1 and 1. So the denominator x grows without bounds. So the function behaves, so the horizontal asymptote goes to 0, not 5. And y equals 5x. It's a linear function, so y equals 5x, so it's a straight line. It'll grow without bounds, and there'll be no horizontal asymptote because it'll grow to infinity, which will not exist. Choice C, y equals 1 over x minus 5. As x equals to infinity, the function behaves as limit x goes to infinity, 1 over x minus 5 equals 0, because the degree of the numerator is less than the degree of the denominator. And choice D, if the degree of the numerator is the same as the degree of the denominator, then it's the ratio of the coefficients, but it's -5, since the ratio of the leading coefficient is 5 over -1. Now the correct answer is choice E. The highest degree terms dominate, so the function behaves as the ratio of the leading coefficients, which is equals 5. So basically, if the degree of the numerator is less than the degree of the denominator, so for example, if it's 1 over x or 1 over x squared, then as limit as x goes to infinity, it'll always reach a value of 0, no matter what. Only if the degree of the numerator is less than degree of the denominator. And similarly, if the degree of the numerator is the same as degree of the denominator, so for example, x over 2x minus 5, then it'll just be the ratio of the leading coefficients, so it should be 1 over 1/2. And if the degree of the numerator is greater than degree of the denominator, for example, if it's 2x squared over 4x, and if it goes to infinity, then it will always go to infinity because the numerator grows larger than the denominator. Problem 2, limit as x goes to pi, cosine x plus sine of 2x plus 1, everything over x squared minus pi squared is A, 1 over 2 pi, B, 1 over pi, C, 1, or D, non-existent. Pause the video if necessary and solve it. Okay, if you learn more calculus, there is a concept called L'Hopital's rule, which will be explored in the next lecture. But since we did not learn that yet, let's use trigonometric identities to solve this problem. The answer is B, 1 over pi. So first of all, we can factor the denominators to get, using difference of squares, to get x plus pi times x minus pi. If you let h equals x plus pi, then cosine x is cosine pi plus h, right? Because cosine x equals cosine 2 pi plus x equals negative cosine h, right? And sine 2x equals sine 2 times pi plus h, which equals sine of 2h. And x squared minus pi squared equals pi plus h squared minus pi squared, which equals 2 pi h plus h squared. So the limit is equivalent to limit as h goes to 0 minus cosine h plus sine 2h plus 1, everything over 2 pi h plus h squared. Notice that the numerator simplifies to 1 minus cosine h plus sine 2h. And 1 minus cosine h using the half angle formula is 2 times sine h over 2 squared, or 2 times sine squared h over 2. Also, using double angle identity, sine 2h equals 2 sine h cosine h. Hence, the numerator becomes 2 sine squared h over 2 plus 2 sine h cosine h. And we can factor the 2 out. And as h goes to 0, sine of h over 2 will go to 0, which is equivalent to h over 2. And sine of h will also go to 0, which equals h. And cosine h will go to 1. So substituting will give 2 times h over 2 everything squared plus h times 1, which equals h squared plus 4h everything over 2. And denominator is still 2 pi h plus h squared. So the limit that we're going to solve is equal to limit h goes to 0, h squared plus 4h everything over 2 pi h plus h squared, and we can simplify this to h plus 4 everything over 2 pi plus h by dividing h on both the numerator and denominator. Remember, h goes to 0 and h does not equal to 0, so we can divide by h. And we can now use direct substitution to give 2 over 2 pi, which equals 1 over pi, which corresponds to choice B. Problem 3. The graph of the function f is shown above. Which of the following expressions equals 2? A, f of 3. B, limit as x goes to 3 minus f of x. C, limit as x goes to 3 plus f of x. Or D, limit as x goes to 3 f of x. Pause this video if necessary and solve it. Okay, so let's look at each of the choices. First of all, f of 3. We can see that f of 3 equals 4, not 2. So A is out. B, limit as x goes to minus 3 minus f of x. So 3 minus approaches from a value less than 3. So indeed, it approaches 2. So B is the answer. Let's look at C and D. C, limit as x goes to 3 plus f of x. It means that we are asked to find the limit as x approaches a value greater than 3 to 3. So like this. And we can see that it reaches a value of 6, not 4. So these are out. Limit as x goes to 3 f of x. Since these two are not equal to each other, we can conclude that this does not exist. In order for limit to exist, 3 minus and 3 plus, the values should be the same. And that applies to all limits, not just this one. Okay, problem 4 is a calculator active question. Let f be the function defined above. F of x equals e to the bx for x greater less than or equal to 2, and 1.5x plus b for x greater than 2. For what values of b is f continuous at x equals 2? So basically, try to solve this problem, pause this video if necessary, and solve it. Okay, so basically what we're asked to find is finding value of b such that f is continuous at x equals 2. In order for f to be continuous, there shouldn't be any breaks or holes, so we equalize these to each other. So e to the bx equals 1.5x plus 2, x plus 2, and we are given x equals 2, which we just substitute x equals 2. So e to the 2b equals 1.5 times 2 plus 2, which equals 5. So basically, we are asked to find values such that 1.5x plus b. So it's not 5, but It should be 1.5x plus b. Sorry about that. So, and 1.5x equals 3 since x equals 2. So basically, we are asked to find values of b such that e to the 2b equals b plus 3. And using a calculator solve function, we get the answer of d. Okay, this was the end of the lecture, and thank you very much for listening, and bye-bye.